So I just want to show you a little bit about our parallel impedances and how to solve for a parallel circuit. This is a little bit further than I expected us to get this semester, but I wanted to show you a little bit of how this would work and show that you can work pretty much any problem now if you understand the phasors and the concept of impedance. So let's look at number 10 in part A here. And if we wanted to find the total impedance, if we had two resistors, let's say in parallel, R1, R2, we would find our total using the equation 1 over R1 plus 1 over R2, right? Well, we're going to do the same thing with our total impedance. So we'll have 1 over, let's say this is Z1 and that's Z2, 1 over Z1 plus 1 over Z2. So what are those impedances? Well, Z1 is a 10 ohm resistor, so that's just 10 plus 0J, or just 10. And the 60 ohm inductor, that is 0 plus 60J, or just 60J. And I'm putting the 60J in parentheses so that that J stays in the denominator, because we don't want that to move, so to speak. We want that to be under the bar in the fraction. Okay, so 60J. Okay, so I'm going to give you the rectangular form of this, which is about 9.73 plus 1.62 times J, or the polar form, which is 9.86 at an angle of 9.46 degrees. Let's do the same thing for our second circuit. Okay, so here we have 1 over 3K plus 1 over 6KJ. Again, put that in parentheses so that that J stays under the bar in the denominator. And then 1 over negative 9KJ. Again, I'm putting all of that in parentheses because I want that whole argument under the bar, or in the denominator. Okay. I didn't put the 3K in parentheses. You can do that if you want, but it's really just 1 over 1,000. Okay, so what you should find here is 2,959 at an angle of 9.46 degrees. Or if you have that in rectangular form, it should be 2919 plus 486J. There's some decimals to that too, but anyway, so that is our total impedance of our circuit. So let's look at actually working through a parallel problem. Now I'm going to find the ZT just like we started out before. So we've got 1 over 12 plus 1 over 10J. Again, if you're having some trouble finding the impedance of these components, go back and look at that again. In polar form, that would be 7.68 at 50.19 degrees. Or in rectangular form, let me just check to make sure this is right. Okay. Should be 4.92 plus 5.9J. Okay, so you can use either one when you go to find I sub S, which is just going to be E over CT. So we've got 60 volts at 0 degrees. And like I said, you can use either form, the rectangular form or the polar form. If you're using either form, really, put the entire denominator in parentheses just to make sure you have the correct answer there. So in polar form 7.81 at negative 50.19 degrees. And you don't have to find both the polar and the rectangular form. I'm just working them both to show you, if you have them right, what that would look like. Okay, so that should be about 5 minus 6j in rectangular form. Okay, so now to find the current through the resistor and the current through the inductor, remember in parallel we have the same voltage drop across all of the elements. So here now we're looking for current. This is a current divider. So IR is simply going to be E over ZR, where we have 60 volts at 0 degrees, over our 12 ohm resistor also at 0 degrees. So we should have 5 amps at 0 degrees there, or 5 plus 0J. For the inductor current, we've got E over ZL, or 60 at 0 degrees, over 10 at 90 degrees. So that should be 6 at negative 90 degrees, which is 0 minus 6J. Now in the rectangular form, it's a little bit easier to see that 5 plus 0J and 0 minus 6J does add up to our source current of 5 minus 6J. If you found this in polar form, you can still add the 5 at 0 degrees plus 6 at negative 90 to get the 7.81 at negative 50.19 degrees in polar form. So keep